for example, A to C, C to E, E to F. This is also a path, and the length would be, in this case, 1 plus 3 plus 1, giving us 5. And there are also other paths here. And the question here is, how do we find the longest path, which means a path having largest length? Of course, we can use a brute force approach by starting at each node and see what is the longest path we can get starting from that node. And we can repeat this for each of the node as a starting point. I think eventually we're going to have the longest path. But I think the complexity in this case would be quite large. So let's think about if we can use a dynamic programming approach to solve this problem. And remember, by using dynamic programming approach, we want to break the original problem into sub-problems. And then we try to solve each of these sub-problems and see how the solution to the sub-problem can help us form the solution to the original problem. I'll give you maybe 2 or 3 minutes thinking about it, and I'll just quickly draw this graph on my screen, and then we will work through it together. All right, let's try to solve it together. The first thing I think what we can do might be, well, we want to consider each of the nodes one by one, like in the coin roll problem. And in the coin roll problem, I think it's pretty straightforward. We have an array of coins, and then we can simply go through each of them one by one. But in this question, how do we know which node we can consider first and which node we should consider second, and so on? Remember, we have topological sort that can be applied on this kind of graph. It's directed graph, it's a cyclic graph. There's no circle here in the graph. And if we apply topological sort, this is one possible outcome. A, C, B, D, E, F, G, H. And I have all the edges already marked in this sequence, and also their weight for each of the edge. Now let's consider if it's possible that we can consider each of the node in this topologically sorted sequence. Now what we're going to have is, for each of the node, let's say, let me first hide the rest of the node. Let's just consider the first node. Now the question I'm going to ask is, if we have a path ending at A, we have a path ending at node A, what is the longest length or longest distance? I think in this case, it's pretty obvious. It should be 0. The reason is that there's no incoming edges from anywhere to A. So if a path ending at A, well, it has to have a length of 0 because we couldn't even find a path. Now let's move on to the next one. Now we have one more node that we want to consider. For node C, what is the longest distance or longest path that end at node C? And looks like in this case, C has an incoming edge. There's only one incoming edge from A to C. So it tells us that if we have a path ending at node C, then it must be coming from node A. And if it's coming from node A, the total length would be the longest path ending at node A plus the weight of paths from A to C. Right, so we have 0 plus 1 telling us that if we have a path ending at node C, then the total length would be 1. Keep going for the next node B. In this case, again, we will be considering if we have a path ending at node B, what is the longest distance we can have, or largest length we can have? And looks like in this case, we have two different scenarios. If we have a path ending at node B, it might be coming from A, it might be coming from C. So maybe we consider each of them one by one. If we have a path goes from, I don't know where, to A, and then A to B, and another case is we have a path from somewhere to C and then C to B. Now we already know that A to B has a length of 3 and C to B has a length of 4. And I think we also already figured out that if we have a path ending at A, the longest distance would be 0. And if we have a path ending at C, the longest distance would be 1. So it looks like in this case, we know that if we have a path ending at B, then if it's coming from A, the longest distance would be 3. And if it's coming from C, the longest distance would be 5. And of course, it tells us that if a path ends at node B, the longest distance we can have is 5. I hope this makes sense to everyone. Let's move on to the next node, D. If we have a path ending at node D, looks like it has to be from node B. And as we can clearly see that a path ending at node B has a length of 5. That's the maximum we can get. Then B to D has a length of 6. So this tells us that the path ending at node D has a length of 11 maximum. Keep going to the next one. Node E, we have two choices. It might be coming from D, giving us 2 plus 11, that's 13. Or we have C coming to A, and if we have a path from C to E and ending at E, then the longest distance would be 1 plus 3, giving us 4. 4 is clearly smaller than 13, so I think the path ending at E must have a longest distance of 13. And then the next node, F. Again, two choices. We may have a path going from somewhere to D and then D to F, or we may have a path going from somewhere to E and then E to F. So if we are coming from D, the total length would be 4 plus 11, giving us 15. And if we are coming from E, I think we can only get 1 plus 13, that's 14. So we only keep the largest value we have. All right, keep going to the next one. For node G, no incoming edges, so we know that if we have a path ending at here, node G, the length would be 0. And for the last node, only one possibility, we come from G to H. giving us the length of 9. Now, what we have here, we have an array of integers, and each integer tells us if we have a path ending at that node, the longest distance or the longest length is stored in the array. So I guess now we should scan through the array and try to find the largest element. I think in this case we find 15 as the largest element. This indicates that the longest distance or longest path we have from this graph should be 15. Again, by using this approach that I just introduced, we don't know the actual path. We only know the length of this path. But if we want to know the actual path, I think we can have an additional array. And the usage, or why do we need this, or what do we need to store in this additional array would be, for each of the value, which is the longest distance we have in the first array, we will also keep track of what is the previous node. For example, for the first node A, there's no path ending at that node, so we don't really care about that. And for the second node, C, we get this 1 because we know that if we want to have a path ending at C and giving us 1 as the distance, as the length, it has to be coming from A. So we're going to record A here, indicating that we are coming from A. And for node B, we get this 5 by coming from C. So we should record C here, indicating that the path ending at B, giving us length equals to 5, must be from node C. Again, for node D, we should record B as its previous node. And for E, I think we record D. And for F, we record D as well. And the value for G, we don't really care because we cannot have any paths ending at node G. And for the node H, we have node G as its previous node. Now, if we know that 15 is the largest or it's the longest length we can get for this graph, then we can also find out what is F's previous node, and we can find it's D. Then what is the previous node? Then we will find B. And what's B's previous node? We'll find C. And then what's C's previous node? We'll find A. Is there a previous node of A? No. So we find that A is a starting point. So this third array, or this last array, gives us ability to backtrack the actual path. So we know that the path giving us 15 as the total length would be from A to C, C to B, B to D, and then D to F, giving us 1 plus 4 plus 6 plus 4 equals to 15 as the longest distance. If we consider the complexity of this approach, we first applied topological sort, and I think we are clear that topological sort needs V plus E as the time complexity. So the topological sort giving us this sequence. Then for each of the nodes, what we did, remember for each of the node we consider if we have a path ending at that node. So for each of the node, we only need to consider all the incoming edges. And for all the nodes, looks like we've considered all the edge exactly once. And of course, since we go through each of the nodes once, we will also have a linear complexity to V here. And at the end, we need to linearly scan through this array to find out that 15 is the largest value. So I think we have another OV. And if we add these operations together, I think we get V plus E as the overall complexity. So this means that in a directed acyclic graph, if we want to find the longest path